Hello my dear students, welcome back to the IMS GATE Academy. As the IMS GATE Academy started the foundation course, the foundation series on the various subjects, like we have selected the fundamental subjects of each branch. In that subjects, most important topics, the fundamentals to those most important topics are going to be discussed in this series. From the computer science branch, the subject computer organization architecture is chosen. So in this subject, so we'll see the fundamental topics, the fundamental understanding of this computer architecture, so that the main classes, the main course you will be understanding in a better way. Chalo, start the session. I hope everything is clear, so that we can start the session. Please comment, all of you. The voice, everything is clear, right, all of you? Okay. So now from this computer organization architecture, I have chosen the topic called floating point number representation. So this topic is one of the major important topic, I could say, from the GATE point of view, because 1 or 2 marks question, like 1 mark question or 2 mark question we can expect. Like that, some other topics also I am going to be discussed. So I am going to spend like 15 to 20 hours on this computer organization. I would like to cover the major basics of understanding the various important topics from this subject. First of all, let me write the topics which I am going to be discussed, so that we can start the session. Fine. So the initially few hours I spent on the floating point number representation, floating point. Then after that we will go to the memory organization. Memory organization. In the memory organization, the various memory components will see, considering the memory hierarchy, like the various memory components, like say main memory, cache memory, secondary memory. So their connection and their performance will observe. The followed by, I will look into the instruction pipeline. Instruction pipelining. So I have chosen the major 3 important topics from the computer organization architecture, that is floating point number representation, followed by memory organization, then we will see the instruction pipeline. So then we will see the instruction pipelining. Okay. So now let us understand the importance of the floating point number representation. Also we see how floating point number represented, how the numbers are represented in this format, we will observe clearly. So chalo, we will begin the session. The first is floating point area. But just before proceeding into floating point area, so what are the basics, what are the fundamentals required to be understand the floating point number representation is clearly. So we will focus now the fundamentals to the floating point number representation. The few things you will study from the digital logic design, but what are the essential required to be get the floating point number representation, we will cover first. So then we will take up the representation of the floating point numbers, what formats are there, most of you are aware of it. IEEE institution has given a standard for the floating point number, like IEEE 754 standard, that is single precision, like double precision, even extended precision is there. So these are the standard formats are there to represent the real numbers in the computer systems. So those things will observe. The prior to these standards, we'll see the basics. The basics means we need to understand very clearly base of the system. Their conversion, those things we will study from digital logic design, but we'll understand what is 1's and 2's complement, sign magnitude representation, their ranges, the representation part we'll see now. Fine, all of you? So you can comment. Okay. You see, all of you, data. So data is there, data or information. This data is majorly classified into two types. One is non-numeric data. non-numeric data. Non-numeric data. The other classification is the numeric data. Numeric data. Non-numeric data comes what? Text. The like alphabets, symbols comes under non-numeric data. The numeric data is integers, right? The numeric data is integers. This numeric data also further classified into two categories. Just I want to specify the floating point area which I want to discuss, right? Where it is false, you see. So numeric data is classified into two types. One is fixed point. We call fixed. So we'll understand what is a fixed point here. Fixed point, numbers are integers, fixed point numbers. Then second is a floating point. Floating point numbers. Understand all of you. So the fixed point, we need to understand what this floating point is talking about, so that we can move on to this representation of fixed and floating point. So if I say the fixed point, please understand all of you, the fixed point says here radix point, radix. So radix point or base point, base system point. So number system points will be like binary point, decimal point, octal point, hexadecimal point here. The fixed point, radix point is fixed here. So radix point is fixed here. Getting my point? So floating, please understand, floating moving here, you know. Radix point. So radix point is moving. So it is not fixed. Please understand all of you. Radix point is not fixed, it is floating. So moving, radix point is moving across the digit. So this is the fixed, this is the floating. I hope you understand the differentiation. Okay. Now, so I want to more focus on what this floating point number representation. This is very important topic from the GATE point of view, because so every year or alternate year we can expect the question from this year, 2 mark question or 1 mark question we can expect from this area. Now, to understand, to learn the floating point number representation, we'll see the some points, some importance points from the fixed point also. So then we can discuss this floating point area. So very good evening, Amit Goyal. Very good evening. So now look here, fixed point. What is this fixed point? Let me write the few points on here. What I said to you, if I say fixed point means radix point is okay. So as I mentioned that radix point is fixed. Radix point is fixed. Radix point is fixed here. Please understand. So there are fixed point here. Two things we need to understand. Integer numbers are there. Integers. Second one is a fractions. For integers, radix point is fixed. Fixed after LSB. What is LSB? Least significant bit. For integers, radix point is fixed after LSB. For fractions, radix point is fixed before MSB here. So what is LSB? Least to significant bit, most to significant bit. I hope you understand. Least to significant bit, this is a most significant bit here. So what I'm trying to say, the radix point is fixed for integers after LSB, for fractions before MSB. So these 2 points you need to be understand. So example if you see, example 1. So 123, if I take the decimal number, see 123. So decimal point is after the LSB. So example, if I take 0.101101, if I take the binary number, fraction number, if you see, the binary point is what? Before MSB, this is a MSB position, MSB position, this is a LSB, least significant bit position here. For fractions, radix point is before MSB, for integers, radix point is after LSB. This need to understand. That's what I said, you know, fixed point numbers now means radix point is fixed. That's it to understand. For a floating point numbers, please understand, for floating point numbers, for floating point, okay, for floating point. So what I was telling, floating point, floating means what is the floating here? Moving here. So radix point is, so radix point is not fixed, means it is moving. So it is moving across the digit. Example, you see, if I take a number 12.45, okay, see, after 2 decimal my point is there, 1.243, so after 1 decimal, so 1234.567, assume that, see. So this point is moving across the digit. These numbers are floating point numbers. You can tell the real numbers. Okay. For dealing with this numbers, separate hardware is essential. Most of the architecture, please understand, most of the architectures to deal with the floating point numbers, separate hardware is there. Separate hardware, because the floating point number, integer and fraction both are there. We have to deal separately. Even some of the architecture, you know, separate processor will be there. So we have CPU, right? CPU. There will be another CPU will be there to only deal with the floating point numbers. And for one CPU for the integers, other CPU for the floating point number. To speed up this operation, the separate processor might be kept into some of the architectures. I hope you understand my point, all of you. Fine. So what I was telling? So we'll look at the floating point area. Before that, we'll spend some amount of time in the fixed point number representation. The basic will cover that. Definitely will help us to understand the floating point number system clearly, ma. Fine. So I hope you studied the number systems. Sir, what are the number systems are there, sir? Decimal. So decimal number system, decimal, and the binary, and third one is octal number system. The fourth one is the hexadecimal. So these are the main, like, number systems, like their conversions. If you are not studied, you will study from the digital electronics point of view, their number system representations, their conversion. Please understand, representation conversions you just cover from the digital electronics point of view. So because another faculty is going to take the digital electronics. Then this generalized this number systems I'll be considering. The representation will see the expression, and the range of the representation will observe. Fine. So generalized I'm taking, not specifically any decimal system I will be not considering, but generalize their representation, this value expression, and the range of the each number system we can observe it. The detailed representation conversion you will study from the digital logic design point of view. So are most of you aware of this representation? We will take that basics also wherever it is required. Clear, all of you? Okay. So look the point here. Let n bit number. So n bit number. Now one more thing you can observe. One more thing also need to be observed here from this point. What I was telling you, fixed point, floating point, both are there, right? Okay. Yes or no? Both are there. What is our focus is here. One more point also you can understand. This fixed point can be, please understand, the fixed point numbers can be unsigned. Unsigned. It can be signed numbers. Signed or unsigned. This floating point numbers also can be again, right? It can be unsigned. Unsigned and signed. Signed numbers. You understand? Signed integer. Okay, getting my point. Signed integer or signed integer, unsigned integer. One more classification also we can observe. This fixed point, as I mentioned, integer, right? Integer. Okay, integer. And second is what? Fraction. That's what I said, Radix point is fixed for integers. Radix point is after LSB. For fractions, radix point is what? Before MSB. There are two things, integer and fraction. Separately we will study. Separately we will study. So look the point here. Look the point, all of you. So let n bit I am writing now, n bit binary number represents let I am just considering the n bit binary number represent the fixed point. First of all, we will take the scenario of the fixed point unsigned integer. I hope you understand. Just before proceeding into the floating point area, let us focus the fundamentals or basics which are required to study that concepts. We will see the fixed point area. Here also we will go with first of all integers, then fractions, and integer fraction can be studied again signed and unsigned way. So both the classification will consider here. Okay. So look at here. Let n bit binary number represent the fixed point unsigned integer. Let me write the binary number. So bit 0, bit 1, bit 2. So n bit b n minus 2, b n minus 1. So n bit number which are 0 to n minus 1. So I am considering this is a binary number. Base of the system is 2. The base of, because I mentioned here binary number. Okay. Base of the system is 2. How many bits are there? N bits are there which are numbered from 0 to n minus 1. This is representing which number, ma? Fixed point unsigned integer number. Is integer number. Okay, integer number represented. Whatever representation you take, there are two things will be there now. Please understand. Two things will be. One is value expression will be there. Value expression. And second one is the range. So range of the number representation will be there. Value expression we can obtain sum of all weights of the digits or weights of the bits, you can say. If it is a binary number, sum of weights of the all bits you have to take it. So that gives the value expression in terms of decimal. Or if it is a decimal number system, if it is octal number system, if it is the hexadecimal number system, what we can say, sum of all weights of the digits I can tell. So that giving what? Value expression. The range, what is the range? Range is going to be covers the minimum value to maximum value. So what is the ranging? The range is, what is the range here? It is covering the value of minimum value to maximum value is representation. We will see the value expression range of the this representation. Which representation? Fixed point unsigned integer. I hope you understand, all of you. Look here, look point here. So for this value expression, first one value expression, look at the value expression, all of you. So value expression, okay. This is a number, right? This is a number for this value expression. Value expression was what I said you? Sum of all bits weight. So what the bits weight will be? So B0 into 2 power of 0 plus B1 into 2 power of 1 plus B2 into 2 power of 2. So dash last bit is what? Bn minus 1 into 2 power of n minus 1. So this is a value expression. So I can write, summation. This we can rewrite. Summation I start from 0 to n minus 1. So each bi, you have to multiply weight of this bit 2 power of I. So this is a value expression. Value expression for what? Unsigned integer number, integer. Here is what? What is the B? B is a bit, right? 2. So this also you can rewrite. This also I can rewrite. Please understand. This also I can rewrite. Summation I equal to 0 to n minus 1 bi into r power of I. Okay, r power of I also we can write it. What is r? R is a base of the system. It can be a binary number, it can be a octal number system, it can be decimal number system, it can be hexadecimal. Okay, for all the things. That's what I said, in our case we'll just focus generalize the number representation, their range will observe. So this is a requirement for understanding the what floating point area. So I hope it is clear. If it is a binary number, this is the value expression it will give. If it is generalized it is for every number system. It is for every number system, this value expression. Okay. So example you understand, see the example for this. Okay. Example, see the example. Okay. 123 is there, is a decimal number system, decimal number system. For this value expression, how to write? So knowingly, unknowingly, we know the concept, we call is a unit place, 10th place, 100th place, right? Unit place meaning what? So 3 into unit. So 3 into the base of the system, how much? 10 power of 0, I'll write unit. This is unit is 3 comes only. So 10th, we call 10th means so 10 you have to multiply. So that's not what 2 into 10 power of 1 plus 1 into 10 power of 2 here. See what I say, this is same only. So B naught into 2 power of 0. Why B naught? Because I mentioned B naught. You have to start from the rightmost. So rightmost digit you have to divide by 0, multiply by 2 power of 0, 2 power 1. So it will go. So same thing applied here. So this is nothing but 3 plus 20 plus 100. So this is 123. Is it not? 123 base 10 or not? 123. This is a value expression. Suppose if I take 101101, so binary number, what is the value expression? 0 into 2 power of 0 plus 1 into 2 power of 1 plus 1 into 2 power of 2 plus 1 into 2 power of 3 plus 0 into 2 power of 4 plus 1 into 2 power of 5. So this gives, so this is 0, this is 2 plus 4 plus 8 plus, so this is 0 plus 32. I hope you understand. This is 40, 46. So 46 is a decimal. See, value expression, please understand, value expression gives the value in decimal, please understand. Whatever a system you take, okay, when you take the value expression for that, so that gives a value in decimal. See, binary number, when I take the value expression, its value is how much? The value of this expression how much? 46. So this, so for this also, value expression how much? 123, because this is same only, decimal number only. This is a decimal number only. Similarly, if I take octal number, when you take the value expression of it, that will give the decimal value it will give. I hope you understand. You wrote down this important, all of you note down this important. Example 3, if I take 162, if I take C 162 or any sample, so 103 if I take, this is a octal number I am taking, octal number. What is the value expression? 3 into 8 power of 0 plus 0 into 8 power of 1 plus 1 into 8 power of 2. So this gives 3 plus 0 plus 64. Is it not? So this is 67. So 67, sorry, this is in 67, right? 67 in decimal. Octal, see, this is the decimal. Number you represented, number represented what? Octal. When you take the value expression, this is what? 60 is the value is giving in decimal. So that value is how much? 67. I hope it is clear. I hope it is clear. So this expression is applicable for every system. This is a generalized representation. So generalized number representation, for that value expression it is. I hope it is clear. Chalo, we'll see the range. Now we'll see the range of the representation. As I mentioned, value expression it is. Value expression example I given. Now see the second one is a range. A range of this representation, range. Okay. What I said, you range is covering value of minimum value to maximum value it is covering, minimum value to maximum value. First of all, take the value expression. From this value expression we can get the range. The value expression was, so I equal to 0 to n minus 1, right? So bi into 2 power of I, this was right? Yes or no? Please understand, for all of I, please understand, if bi, all bi's are 0, for all of I, all bi's are 0, then see what happened, this value expression, 0 into 2 power of 0 plus 0 into 2 power of 1, so plus last digit is 0 into 2 power of n minus 1, last bit is this only, right? So this giving 0 or not? Now understand, value of minimum, this number represents what? 0. I hope you understand. Range is covering from minimum value to maximum value. What is the minimum value it is? Minimum value it is 0. Minimum value it is 0. So now look at the, suppose maximum value, how this maximum value represent? Same value expression, summation I equal to 0 to n minus 1 bi into 2 power of I, 2 power of I. For all of I, all bi is equal to 1, all 1. Now see the value expression, 1 into 2 power of 0 plus 1 into 2 power of 1 plus 1 into 2 power of 2 plus 1 into 2 power of n minus 1, right? N minus 1. I hope you understand. So this gives what? This is 1 plus 2 plus 4 plus 2 power of n minus 1. You hope you understand, right? So this is a value expression, So this, take the summation. If I apply the geometrical progression, so this entire summation gives how much? 2 power of n minus 1. I hope you understand. So this gives what? 2 power n minus 1. Now range. So range is covering 0. Minimum value is what? 0 to maximum value is what? What is maximum value? 2 power of n minus 1. So this need to be understand. Note of it clearly. So this is useful for us. Many things, many places, not only in the subject, in any subject, wherever you are dealing with the numbers, so binary integers. So now when you have n-bit number, n-bit binary number is there, what is the minimum value maximum is possible? Means 0 to 2 power n minus 1. So this also I can generalize into 0 to r power of n minus 1. So this is a range. What is the range? Range for what? So this is a range for what? All the systems are binary number, it can be octal number, it can be decimal number, it can be hexadecimal number. Fine. So see the example for this. See the example. Okay. 0 to r power of n minus 1. So I am taking the r as a binary. Binary system, assume that. N equal to 3 bits if I take. So 3 bits range what? 0 to r is what? Binary only, 2 power of 3 minus 1. So this value is how much? 0 to 7. Okay, 0 to 7. 3 bits. If I have a binary 3 bits, 0 to 7 number represented. Total how many numbers are represented? 8 numbers. So many times, please understand, all of you, this is basic, very essential things to understand the range of the system, a range of the number system, that is binary number system, because many subjects, not only this computer organization, operating system point of view, even any other subject point of view, whenever you are dealing with the binary numbers, the range comes matter. Such cases need to be defined. So you need to understand, all of you. So 0 to 7 number represented. Suppose 3 bits if I take it out of 3 bits, 0 0 0 0 0 1, sorry 0 0 1, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, 1 1 1. See, when all zeros are, sorry, all 3 bits are, see, when all 3 bits are 0, this value is representing 0. When all 3 bits are 1, this value representing 7. So it is covering the range from 0 to 7. Binary pattern is like this. Point is clear? Please you can comment if you have any doubt, ma. Please you comment if you have any doubt. Yes. So similarly, if I take suppose if I ask you to write, this is the first example, right? The first example. Second example, if I take n equal to 10 bits. So base of the system is 2 binary only. What is the range it will cover? Gives 0 to 1023. So 0 to 1023. This is the range. Correct? Suppose if I ask question, example 3. How many binary bits required? How many binary bits required to represent how many binary bits required to represent first one under this first one 100. Okay, 100 is a decimal number, please, decimal number 100 is there. How many binary bits required to this represent this 100? That's a question, you can answer it. Somebody answer it. How many binary bits required to represent 100? So we got a basic idea. What is the basic idea? 3-bit number can represent 8. So how is it? So 0, 2 power 3 minus 1 only, 0 to 7, total is 8 possible. 5 bits are there. 0 to 2 power 5 minus 1, 31, 32 total. 6 bits 64, 7 bits 128, right? 7 bits 128. But my question is that 100 numbers I want to place, how many binary bits required? If you have a 6 bits, you can maximum represent 0 to 63 only. 7 bits is the range is 0 to 127. Now 100 falls under 0 to 127 range. So definitely I am writing n value. Required how many? 7 bits required to represent 100. I hope you are understanding. Reverse, if the bits is given, they can ask a range. Range is the given, we can ask how many bits required to represent. Suppose, please understand, B, like B I am asking, 523 are there, 523 is a number. How many binary bits required to represent this one? Basic questions only I am asking, because see, sometime we may lag with the basics actually, some difficult concept may understand, sometimes complex topics also you may get to know, but sometimes you are missing the basics. The objective of this session is to understand the basics of any particular topic, anything. Are you getting my point? The floating point area is there, entire analysis we will see. Prior to that, understanding this topic, what essential required, basics required to get here. Some few students it may be looking like, sir, too basic, sir, this one, because it is already know. If you know already this all, I think this is well and good, so that you will save the time when you are understanding other topic. If somebody knows or do not know the things, so definitely this is going to be help lot. Fine. So 523, tell me now. Similarly, you can go 7 bits, 128 numbers you can represent, 8 bit, 256 numbers you can represent, 9 bit, 512. So now it is more than 512. So I have to go next range. Simply you have to apply the log of this one, approximately log of this one. So log value, suppose if it is round up to any 128, 256, 512, 1024, 2048, so that you can express power of 2 something, you can get it. But my point is that you go with this way only. What is the way? 3 bits has 0 to 2 power 3 minus 1, 4 bits 2 power of 4 minus 1, maximum number 0 to that value. Now how to think, sir, 523, how many bits required? The idea is understand 7 bits 0 to 127, 8 bit is 0 to 255, 9 bit 0 to 511, but 523 falls next number. So 10 bits is there 0 to 1023. So this comes under, so 10 bits I can say, 10 bits required to represent here. Clear? So I hope you understand this one. Suppose if another example, if I take another example, base of the system R is 8 octal number, and number of digits are 3. If I take number of digits are 3 digits. So digits 3, because octal system we have a digit 0 to 7. Now range will be what? What is the range? So range will be 0 to 8 power of 3 minus 1, because number of digits are 3, 8 power of 3. So this gives 0 to 0 to, so 511. Okay, now understand. 0 to 511, total 512 numbers can be represented with 3 digits of the octal number. 3 digits of the octal number. But one more thing you have to understand here. Here 511 which number we got, right? This 511 is not a octal number, please understand. The 511 is a decimal value only. How, sir? Please look here. Suppose octal system if you take, okay, octal system, okay. 3 digit number is there, 3 digits are there. How to write 0, 0, 0, 0. So 0, 0, 1, like 0, 0, 2, 0, 0, 3, 0, 0, 4, 0, 0, 5, 0, 0, 6, 0, 0, 7. After that 0, 1, 0 it will come, 0, 1, 1. Like this, no, somewhere 1, 0, 1, 0. So it will go to 7, 7 only, please understand. It cannot come 511 actually, because see, my point is that, so 0, 0 to 777 is there, right? These are the octal numbers which able to represent 512 numbers which are from 0 to 511. So these many numbers can be represented. See, here we got 777. Now 777 is not a decimal number, please understand, octal number, octal. So 3 digits of octal is there, 0, 777. The total will be there, the total will represent in decimal how many? 512, which are 0 to 511. So whatever range you got, this is not octal range, this is a decimal number size. This many decimal numbers you can represent in a octal number system, because so decimal we have a how many digits? 10 digits are there. In decimal 10 digits are there. In octal only 8 digits are there, means so less digits are there, it will represent more. More means what? More numbers required. See, 7, 7 required. Otherwise, this many numbers we can done in a 512 only, because the decimal system is high. I hope you understand the intuition of this representation here. Okay. Suppose example, another example. So I'll write example. Okay. Example 5. You see the otherwise I will write example here only, because that example I written here. Look at example 5. Okay. N, suppose base of the system if I take R, base of the system 16 if I take, okay, and number of n equal to 3 if I take it. What is the range? So range is 0 to 16 power of 3 minus 1, right? 16 power of 3 minus 1. So 0 to 16, how to raise it? 2 power of 4 can 12. So this value is 1000, sorry, 4095. 16 power of 3. 16 I can write 2 power of 4. So 2 power of 4 if I write 2 power of 12 becomes 2 power of 12 value is 4096 minus 1 4095. See, this many numbers it will represent in this range of 3 digits of the hexadecimal. Hexadecimal 3 digits are there. Hexadecimal 3 digits are there. How many number representing? 4096. See, hexadecimal is a bigger size than the decimal number, right? But you know how pattern goes here, hexadecimal. Hexadecimal pattern 3 digits has 00, 001, 002, like this, no, 009, after 9, 10, 10 how to write? So this is A, right? This is B, this is C, this is D, this is E, this is F, right? F, yes or no? F. So like finally what? F will be there, right? Now 0 to this FF, how many numbers, number of digits, how many are there? So number of, like how many numbers will be there? 4096 numbers in decimal, which are numbered from 0 to 4095. Because this size is, hexadecimal size is large. We have a 16 digits are there, so that it can represent more numbers with a less number of digits. Similarly, you understand, decimal having the more digits, so that it can represent more number than octal number. That's what difference you got, you see, 777. Here is 512 showing that. So I hope you understand the intuition of these ranges here. Okay. So what is the conclusion? Simply any number system is a 0 to r power of n minus 1 is a integer, unsigned. Unsigned meaning what? Positive number ranges. Many situations, please understand, in many situations you will be getting the questions like, what is the maximum number you can write it, what is the minimum number you can write it. So I hope you understand with this example. So now move on to the unsigned fraction representation. Fraction, how can I represent it? What is the range of the fraction, we'll see, right? Now we'll see the second one. What I said you, let n bit binary number represent fixed point unsigned fraction. We'll see this unsigned fraction. Okay, the first I discuss the integer, then we'll say fraction part. So let I'm taking the fraction. So a, a1, a2, a3, a4, an is a binary number. So fraction, you know, right part of the point, binary number. Fine. What is it for integer? MS, like radix position is after LSB. For fractions, radix point is what? Before MSB. This is the MSB bit, most significant bit this is. So this is what LSB, least to significant bit is. This bit is more, this bit is less. That's always least significant, this is the most significant. So this is a number which is representing the n bit number, representing the fraction number. Which fraction number? Fixed point, unsigned fraction, positive, unsigned positive fraction. Since I told you, so any representation has two things. One is value expression, second one is the range. One is value expression, second is the range. What is the value expression is giving? The weights, sum of weights of the all bits or digits we can tell. Sum of weights. Okay. Suppose if let me write the value expression for this number representation. Value expression, please understand. For fractions, for integers what we did? Divide the weight of the system. Integers, we multiplied the weight of the system for each bit. For integers, right? We did. For fractions, what you have to do? Divide the weight of the system for each digit. We have to divide, not multiplication. So look this now, A1 is there, first bit is a A1 I have taken, because fraction side first bit cannot be. So I cannot take the 0, because 0 multiplication all, because we started with 0 previously, but we will start with 1 only for fraction numbers. Because if I start with 0, what happens? The division is undefined, right? We have to divide, right? So A1 into A1 by, so A1 is a digit, bit fraction bit by divided by base of the system into binary. Okay, 2 power of, should I write 0 or 1? It should be 1, not 0. Getting my point? Plus. So simply, otherwise I will write like this. No, simply I will write a1 into 2 power of minus 1. I will write it. 2 power of minus 1 I will write. So 1. So a1 by 2. 2 power of 1 is 2, right? Send upside, minus 1 became. Plus second bit a2 into 2 power of minus 2 plus last bit is an into 2 power of minus n. So this also we can write, simplification. We can write I equal to 1 to n only. So each bit ai you have to multiply 2 power of minus I. Multiply, I should write divide by its weight. That I am writing 2 power of minus something I am writing. But we do division. There we did multiplication for integers. For fractions you divide by the weight of the system. So I hope you understand. This is the value expression for what is the value expression for what? It is for what is it? It is a fraction, unsaid fraction. This also we can rewrite, generalize with all the system. Value expression I equal to 1 to n ai into, instead of 2 I am writing r power of minus I. R power of minus I. Okay, what is r here? R is base of the system. It could be binary, it could be octal, it could be decimal or hexadecimal. I hope you understand. Just need to be substitute in place of r 2, 8, 10, 16. So this generalized expression for all the number systems. So I hope you studied this also from decimal point of view, but just taking in terms of generalization for all the system. Our major focus goes for representation, that's why getting the value expression and looking into the range of these number system. Correct? Number system is this representation. Fine. Now see the value expression we got for this number system. Value expression, this is a value expression, generalized I written. Now we will see the second one is a range. What I said you range? Range is covering the minimum value to maximum value. So this also we obtain from the value expression only. What is the value expression? Summation I equal to 1 to n, each bit ai multiply by 2 power minus I is given at minus I. For all of I, all ais are 0. All ais are 0, nothing but all bits are 0. If all bits are 0 means this is giving 0 or not. So value of minimum is 0 only. Value of minimum 0 because all ais means a0. So you see the now here you understand. This a1 0, a2 0, a3 0, like all an 0. This entire thing is what 0 only. So that is giving the 0. The minimum value was 0. So now you see the value expression to get the maximum value. Summation I equal to 1 to n ai into 2 power of minus I. Correct. For all of I, all ais, if I take 1, all are 1 means what happens you see now? A1 is 1 into 2 power of minus 1 plus 1 into 2 power of minus 2. So plus 1 into 2 power of minus n. This is the value. This is the value expression, right? Value expression. Now, so this if I write it 2 power of minus 1 plus 2 power of minus 2 plus 2 power of minus 3 plus 2 power of minus n. Yes, somebody give the expression. If I take this summation, so this we call value of maximum. Tell me the summation of this series. Tell me the summation of this series. So how much it will give? Somebody please respond. Somebody respond. I am expecting the answer for this range. The range is summation of this part. Summation of this part. Yes. Look here how we can obtain it. I am just a little interested. Look here till n is there n. Okay. So many ways like you apply. If you get a direct formula, you apply and get this maximum value, or some other way also can do it. So what I will do, suppose this series I want to extend. If I extend, what is the next term? 2 power of minus n plus 1 or not? Yes or no? Plus 2 power of minus n plus 2. So this series can be extended infinity or not? Till infinity? Yes, infinity series or not? Yes or no? Now if I ask you sum to infinity in geometrical progression, sum to infinity, what is the expression? A by 1 minus r or not? A by 1 minus r, yes or no? What is a value? A value is 2 power minus 1. What is the r value? R value also 2 power minus 1 only will get. Substitute, what it will give? So this value of maximum, A value, like A value 2 power minus 1 by 1 minus 2 power minus 1, simplify. So this will give 1, correct or not? This is giving 1. But point to understand, So let me, I am rewriting here. So this we got 1, but here it is not, our answer is not 1, because see, so till here only we interested, this extended to infinity to get the simplicity, just extended to infinity. But our value is here only, that part I don't want. So means total summation given me, see, from here to infinity, total summation given to me what? 1. Correct or not, all of you? Total is 1. But our series what? Till n only, right? So this portion is extra. This portion is extra or not? This portion is extra. Okay, this portion is extra. So this is error. Okay, error. So I have to subtract to get this my maximum value. I am writing value of maximum equal to 1 minus this error part. What is error here? What is this error? Error is 2 power of minus n plus 1 plus 2 power of minus n plus 2, right? So till what? Till infinity it is there, right? That's only. So what I will do, this, can I take the common 2 power of minus n, can I take the common? If I take the common 2 power of minus 1 plus 2 power of minus 2 plus 2 power of minus 3, so till it is infinity, right? Yes or no? This give infinity or not? Now see, all of you, 2 power of minus n, what is this series gives? So this series is nothing but this series only entirely. So that has given how much? 1 only. 1 or not? Yes or no? Now see, this given 2 power of minus n. Okay. Now, so value of maximum value how much? 1 minus error. How much error portion you got? 1 minus 2 power minus n you got the portion. So now range of the fraction, unsigned fraction, 0 is the minimum. Maximum how much you got? 1 minus 2 power of minus n is the range. All of you, I hope you understand the range of the fraction integer. Range of the positive or unsigned integer is 0 to 1 minus 2 power minus n. I hope it is clear. So as of now, 2 representation we did. One is unsigned integer, unsigned fraction. Both the value expression, both the ranges we observed. Okay. So now this also we can generalize range for all the system 0 to 1 minus r power of minus n. Can I write it or not? Yes or no? What is the r here? R is the base of the system. It could be binary, it could be octal, it could be hexadecimal, it could be decimal. So this is a generalized thing. So now see all of you. So now what I am trying to say, integer, right? Integer, okay, integer. What I discuss, I am telling integer, okay. Sorry, integer, and second is a fraction is there, right? So two things we discuss. Which integer ma? Plus unsigned. Unsigned means this only. Unsigned integer. So two things we discuss. What is two things we discuss? Value expression. What is the value expression? Summation I equal to 0 to n minus 1 bi into 2 power of I. Yes or no? Range also we discussed. What is the range? So we proven 0 to 2 power of n minus 1 we proven. For the fraction, what is the value expression? Summation I equal to 1 to n ai into 2 power of minus I. Yes or no? What is the range for this? So 0 to 1 minus 2 power of minus n. I hope you understand. So this is a generalized things which we discussed so far. Two aspects over: signed, unsigned integer, unsigned fraction. Now we move on to the signed. Suppose if signed integers, how they are represented. The third aspect of the basics part we'll see signed part, right? Then once done, little we'll see some problems on this. then we can move on to the what floating point area. So look at let n bit binary number represents fixed point only, it is signed integer. I am writing the binary number ma. Look, see, B0, B1, B2, Bn minus 2, Bn minus 1. Right? This is a number. Okay. What this number is representing? So this number is representing fixed point signed integer. Signed number, signed integer. Okay. So one thing you need to understand, this is what LSB, right? Least significant bit, right? So this is what MSB, most significant bit. Okay, fine. Least and most, most and least. Clear. Now, signed number, right? Signed. So signed number integers, please understand, for each number sign need to be represented. For each number, sign of a number required to be represented. What you will do, so please understand. MSB bit is there, right? This MSB bit, all of you please understand. MSB bit, okay. So this MSB bit, okay, MSB bit is representing the sign of the number. Please understand. Sign of the number or integer. Getting my point? Okay. So this MSB bit Bn minus 1, right? Bn minus 1, okay. If it is 0, please understand, okay. So 0 nothing but it is a positive sign, okay, positive number. Positive sign nothing but positive number. If sign bit is like a Bn minus 1, MSB bit is, if it is 1, indication negative number, ma. So negative integer or negative number, okay. 1 and 0. 0 for positive integers, 1 for negative integers. I hope it is clear, all of you, right? So what you have to understand, there is no extra bit, only this last MSB bit is only indication. Now understand, remaining magnitude is only representing the value. This is chosen for what, giving the sign only, fine. So now please understand all of you. So I am writing one point, to represent, okay. So to represent, please understand, to represent signed, these are the signed integers, signed, okay. Signed integers, we have, okay, we have 3 types of notations. So 3 types of notation, we have 3 notation to represent the signed integers. One is signed magnitude, ma. The second one is a ones complement. Second sign ones complement. Third one is a twos complement. Okay. So what I am trying to say, the 3 integers, please, 3 notations, all of you understand. 3 notations are specifically used for representing the sign integers. Getting? Sign, it could be positive sign or it could be negative sign. Sign we have to represent here. So let us observe each notation clearly, how they are going to represent. Their ranges also, their value expression also, we will see. Getting, all of you? So now look this, all of you. Look, all of you. Okay. Suppose, look all of you clearly. What I am trying to do, example is here. Example, some number, x number is there, okay, x number is there. 5 is there, no, plus 5 is there, positive 5. How this 5 is represented by 3 notations, okay. Sign is there, what is sign? Positive sign is there. Suppose let's take this also, minus 5 also there as well, x equal to minus 5 also. We will see how positive sign is represented, how negative number is represented among 3 notations. Look here. First one is sign magnitude, right? SM I am writing. Okay, sign magnitude. let me take 4-bit number, because 5 means 101, I can write it, right? Sign I am writing. Sign means positive. As I mentioned, positive is there, 0 you have to write it. Okay. So go with the ones complement, okay, ones complement. So ones complement also will represent 101, 0 only. So 2's complement, 2's complement 0, 1, 0, 1 only, please understand. So no, please all of you do not misunderstand yourself, sir. One's complement means you have to complement it, right? 2's complement, sir, 2's complement nothing but 1's complement plus 1. No, we are not finding the value of 1's complement value or 2's complement value. These are the notation to represent the numbers here. 1's and 2's complement are the notations, or sign magnitude and 3 notations are used to represent the sign of the numbers. Sign could be positive sign, negative sign. Getting here, positive sign. For all positive integers, you can note of it one line. For all positive integers, all 3 notations have the same representation, no difference at all for positive integers. For all positive integers, you see, what are the positive integer you take, and this all 3 notations are the same pattern, no difference at all. Now look at this. For negative numbers, how negative numbers sign magnitude will represent? 5. You read it sign magnitude. See, the notation says sign magnitude. What is the sign? Minus. Minus how to write? 1 only. What is the magnitude? 5. 1, 0, 1. That's it. Sign magnitude says write the sign, write the magnitude. That's it. No difference. So nothing to do with this sign magnitude. Whatever number is there, minus 25. If I ask sign, what minus? Write 1. 25, write the binary. That's it. Magnitude. So when it comes to 1's complement, 1's complement says that, please, 1's complement we can write through sign magnitude only. Look at the sign magnitude number 101101. This is MSB bit, right? MSB bit, right? MSB bit. Okay. MSB bit 1, right? You keep 1 as it is. Remaining magnitude is there, right? You invert it. What is invert? 1 becomes 0, right? 0 becomes 1, 1 becomes 0. I hope you understand. So 1010 is the 1's complement representation of 5. 1010 is the 1's complement representation of 5. Other way you understand, 1010 you got in terms of binary period, this 10. 1010 is 10 or not? 1010 is a binary number, the value is 10. So 1's complement of 5 is 10 only, because 1's complement with the 4-bit ranges, if you are able to get that point also clear. 4-bit number what? 0 to 15 you will write. 15 minus 5 almost 10, 101. Like this you also understand. Meaning is same. 1's complement of 5 is 10 like this. I hope you get it clear. So if you are not able to understand that point, you leave it. Simply what you obtain from the magnitude, sign magnitude, keep sign as it is, remain a magnitude, invert it. Invert it means apply the NOT gate. 1 becomes 0, 0 becomes 1. That's it. Clear? Next one, 2's complement. So 2's complement very simple. So 2's complement you can note of it all. 2's complement can be obtained. Whatever results comes from 1's complement, add it 1. That's it. Add it 1. I am adding 1 0 1 0 1 1 0 1 1. That's it. This is sign magnitude representation. This is 1's complement representation. This is a 2's complement representation of a minus 5. Clear? Plus 5 represented same. Minus 5, see, all 3 notations having the different pattern. See, 1101, 1010, 1011. All are 3 different pattern. Means 3 notations having the different pattern for all the numbers. We'll observe now properties. Properties of all 3 notations we'll observe now. We'll do little comparison study about these 3. But what is the way of representation? Simple. I said sign write down, magnitude write down. When it comes to 1's complement, look at the sign, keep sign as it is, magnitude invert it. Whatever you obtain from the 1's complement, add 1, that gives the 2's complement value. That's it. Fine. So now see some observations here. So point wise I will write, you can note of it all of you. 1's complement, okay, 1's complement is there, okay, 1's complement, okay, 1's complement and sign magnitude, SM is sign magnitude, please understand. So both are having same range, getting same range is there, okay. N-bit number if I take, if I represent the one n-bit number in these two notations, range is same only, range is same only. I will show with example, no need to confuse, but note of it this line, covering same range and having the same range, okay. This one important point. Second important point, please understand, okay. This 1's complement and sign magnitude, okay, sign magnitude both have, okay, two different notations, two different, okay, two different representations, two different representation for 0. I hope you understand, okay, 0. 1's complement, sign magnitude having the two representation for 0. 0 represented by two ways, each of them. This is second important point. So third point I am writing, please understand. So now 2's complement is there, okay, 2's complement, okay, 2's complement has one representation, please understand, one representation for 0, okay. This is the third important point. Sign magnitude and 1's complement having the two different representation for 0, but while 2's complement has only one representation for 0, we'll observe. So that is a reason it has only one representation, that is a reason in 2's complement, please, 2's complement notation, okay, one extra number is there, one extra negative number, I am writing, so write a negative number, so minus, one extra negative number is there in its range, okay, range. So this is another important point. What I am trying to say, because of it is having only one 0, so that it is covering more range in negative portion comparison to 1's and sign magnitude. That is a line it is talking about. I will show with example, clear. So next point, next important point, 1's complement and 2's complement, okay, both uses same hardware, okay, hardware for addition, okay. Second is subtraction, okay. For addition, subtraction, the hardware used in 1's complement, 2's complement notation is same, both use the same hardware, fine, both use the same hardware. And second point, so while sign magnitude uses different hardware, okay, hardware for one is addition, okay, second is subtraction, okay. When you do like, sir, what is addition subtraction, sir? Because see, when you are dealing with a signed integer, addition subtraction, arithmetic operations signed integers, please understand. Now we have to use this notation to represent them. That's what I am telling you. 1's and 2's complement having same hardware, while sign magnitude having a different hardware for addition and subtraction operation. That's important, need to be understand. Next one. So next important, see now, 2's complement is faster than 1's complement. So 2's complement arithmetic operations, year end, 2's complement arithmetic operations are faster. So write in otherwise simply 2's complement is faster than 1's complement for arithmetic operation. Now for arithmetic operations. Why it is faster? I'll tell you. Why it is faster? I'll tell you. Okay. So 2's complement faster means 1's complement slower. Why it is slower? 1's complement. Okay. So 1's complement required correction for end around carry. Correction for end around carry. That is the reason it is required one extra operation. So 1's complement arithmetic is slower in comparison to 2's complement arithmetic. So what this line says, example, please see all of you. 1 0 1 0 1 is there, something 1 1 0 1 is there. Okay. Assume that these two numbers are 1's complement. Okay. 1's complement notation is there. Assume that. So which are in what? 1's complement notation. This also represents 1's complement. This also represents 1's complement. Assume that. When you are performing the arithmetic operation on 1's complement numbers, so 1 plus 1, 1 plus 1, 2, 2 means 1 0, 0 sum, 1 carry, 1 plus 0 plus 1, again 1 0, 0 is sum, 1 carry, 1 plus 1 plus 0, 1 carry, 1 plus 1 plus 1, 1 carry. Please understand. Now, when you are performing 1's complement arithmetic operation, if you get the carry need to be performed, no addition to this results you have to do like this. We call end around carry operation required. So 0 plus 1, 1 0 0 1. This is our correct results. If you are not adding this 1 to here, that is giving the incorrect results, ma'am. So correction is required. Please understand. This is what we call end around carry. So carry need to be added to the results. When you perform the arithmetic operations on 1's complement. Suppose same operation if I perform in 2's complement, please understand. 2's complement 1 0 1 1 1 1 0 1. Okay. These two numbers are represented in 2's complement notation. Assume that. Then addition how goes? 1 plus 1 0 1, 1 plus 1 0 1 0 1 1. You will get a carry, right? This is a carry. In case of 2's complement, ignore the carry. No effect on the results. In 2's complement arithmetic operations, if you get the carry, ignore it. There is no effect on the results. You can verify. Definitely you can verify. So correction is not required. That's the reason I said you arithmetic operation on 2's complement number representation is quite faster than the arithmetic operation in 1's complement notation. That's what I said you. 2's complement is faster than 1's complement for the arithmetic operations. I hope it is clear, everybody. So you can definitely ask me the questions, or if you have a doubt. If you have a doubt, any doubt is there, just let me know. Fine. So these are the observations we made between them, between three notations, right? So one more thing, one more important thing. Once, please understand, sorry, I'll write it. Sign magnitude comparisons is sign magnitude and 2's complement, okay. So 2's complement notations, notations are weighted systems, please understand, weighted system, binary code decimal also weighted system. Some systems are non-weighted system. I hope you studied the weighted non-weighted system from the digital logic design, correct? So these are the weighted system meaning weight of a digit we are considering, while 1's complement, so while 1's complement is non-weighted system. This is very important theoretical point of non-weighted system. So if I say weighted system means for this, please understand, value expression will be there. For non-weighted system, value expression will not be there. This also you can understand, all of you. Weighted systems having the what? Weights we consider means value expression is there. Non-weighted system, no value expression. Sir, how you are obtaining? Simply inverting, right? 1's complement, invert of the whatever the existing is there. Inversion. Apply the NOT gate. That's what non-weighted system. So next, one more important point. So if you are using the sign magnitude notation, please understand. If you are using the sign magnitude notation for arithmetic operations, sign bit will be there, right? Sign bit sign bit will not participate in the computation, will not participate in the computation, okay, getting my point? In sign magnitude notation, sign bit will not participate in the computation. Suppose 1101 is there, assume that now 10111, suppose there. These two numbers are represented in sign magnitude notation, assume that. When you are performing 1 plus 1, how much? 0, 1, right? So this is 1, 1, this is 0, 1, 1 plus 1, 0, 1, okay. Now see, so these are MSB bits are 1, right? MSB bits are 1. The sign bit only, right? Sign bit. These sign bits are not participating in the computation. See, now 1 plus 0 plus 1 carry we got, so now 0, 1. So till this only. Now you know this is a sign bit. Carry bit came into sign position. Carry bit came into sign position. Indication the overflow here. Carry bit came into under sign position. Sign bit, these are sign bits, please understand. Sign magnitude only there. So sign bit will not participate, but otherwise in 2's complement notation, sign bit will participate. Here it won't participate, no, please understand. So that is one important point we notice. So now 1 plus 0 plus 1 is the result of 0, 1, 1 carry. Carry comes under sign bit. So this indication the overflow in case of sign magnitude notation. Clear? So this important point is clear, all of you, whatever I discussed here. So comparison we observed from sign magnitude 1's complement and 2's complement notation. Clear? So few things let me write down. So suppose if I consider, sorry, look all of you. Let me write these some more numbers to understand the between the sign magnitude 1's complement, 2's complement, all of you. You see now. So I am writing the decimal first. Decimal, okay. Next followed by SM is sign magnitude, okay. Followed by 1's complement. 1's complement followed by 2's complement, look all of you. So plus 0, plus 1, plus 2, plus 3, plus 4, plus 5, minus 0, minus 1, minus 2, minus 3, minus 4, minus 5, assume that, okay. Now let us see how these numbers we can write in a 3 different system, though I given, but once again we will see, okay. 4-bit number I am considering, okay. What I write? So 4-bit number, 4 zeros only, plus 0, all zeros only. What I said you all of you, for all positive numbers, all 3 notations have the same pattern, no difference. Plus 1 means what? 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1. I hope you are understanding. Plus 2, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0. Plus 3, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. Plus 4, outer plus 4, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0. Plus 5, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, plus 5. See, no difference sign magnitude, no difference 1's complement, no difference 2's complement for all positive integers. I hope it is clear. When it is comes to negative sign integers, all 3 representation have the different things. Observe here. Minus 0, how to write minus 0? Sign magnitude says what? You write the sign magnitude. What is magnitude? 0, 0, 0, like this. Sign magnitude. Getting my point? So write the sign magnitude what? So let me write, use a different color. Okay, okay. Minus 1, minus means sign is negative. So minus indication, Sign means order, 1 you have to write, 1 means 0, 0, 1. So for what? This is 2, how to write 2? So minus 0, 1, 0. Minus 3 how to write 1, so minus means 1, 0, 1, 1. So see, sign magnitude, sign magnitude. So this one 4 how to write? 1, 1, 0, 0. 5 how to write? 5, 1, 1, 0, 1. I hope you understand. Writing the negative numbers in sign magnitude. Now see 1's complement. What I say 1's complement? You see the sign magnitude, complement. How is the complementation? Keep sign bit as it is, keep sign bit as it is. Remaining bits you have to complement it, like no. 1, 0 becomes 1, 0 becomes 1, 0 becomes 1. Now see, keeping sign bit as it is, 1, 1, 0. Now I am keeping sign bit as it is, 1, 0, 1. Keeping sign bit as it is, this becomes 1, 0, 0. Keeping sign bit as it is, 0, 1, 1. Keeping sign bit as it is, 0, 1, 0. So this is the 1's complement of this numbers, 1 complement of this number. Other way you understand. Okay, Nikhil, just I'll consider it. So you're not able to see, right? You're not able to see. You're not able to see, right? After this 4. Okay, let me write it next slide only. So till minus 4 only I'll write it. Till minus 4 only I'll write. Okay, fine. So I hope it is clear. So till minus 4, this also fine because the remaining things numbers similarly. Okay. So minus 4, how I written? I am repeating. Sign magnitude. Sign is what? Minus. For minus you keep it 1. Magnitude is what? 4. 1, 0, 0. And 1's complement, keep sign as it is and invert the bits. So 1 becomes 0, 0 becomes 1, 0 becomes 1. So now look at the 2's complement. What I said, 2's complement? Whatever you obtain from the 1's complement, add it 1. So this see, triple, all 1's are there. 1, 2, 3, 4 1's are there. You have to add 1. What? 1 plus 1 how much? 0. 1 carry. 1 plus 1, 0, 1 carry. 1 plus 1, 0, 1 carry. 1 plus 1, 0, 1 carry. So in this is a 2's complement arithmetic, you have to ignore this carry, ignore this carry, ignore this carry. So this giving what? 0, 0. Okay. So let me write it. This is 0, 0, 0, 0, 0. Fine. So this number, so this plus 1, so this becomes what? 1, 1, 1, 1 it will give. So now whatever you obtain from 1's complement, add it. So you are adding 1, 1, 1, 0 it will come. I hope you are understanding. 1, 1, 0, 1 plus 1. 1 plus 1 meaning what? 2, that is right. 1, 0, 0 sum, 1 carry. This is 1, this is 1, 1, right. Triple 1, 0, we got it. So this one becomes what? 1, 1, 0, 1. So this becomes what? 1, 0, 1, 1 plus 1. 1 plus 1, 0, 1. 1 plus 1, 0, 1, 1, 1. So this gives 1, 1, 0, 0. So I hope it is clear. I hope it is visible also. Everyone, please respond. So what we learn here, how to write the sign magnitude, 1's complement, 2's complement for the different numbers. So whatever type of question comes, we are able to write it, right? Now we'll see. Now we will see the range of the different what number systems like sign magnitude, 1's complement, 2's complement. So what we learn here, to represent the negative numbers or sign integers, we have 3 notations: sign magnitude, 1's and 2's complement. The differentiations also we observed clearly with the points I mentioned. Now we have seen how to write the numbers in 3 notations also we observed. Now, so before going to see the ranges of these three notations, let us see the extension process, sign extension. What this sign extension is talking about, we'll see. Then sign extension process we'll see. Then we'll see some questions from this area also. Look all of you. Sign extension. What this sign extension is telling. So placing the small value into large register is a sign extension. Placement of the smaller number into larger register. So this will not, please understand, this will not, either it will not change the sign of a number, or value of a number that I mentioned. Sign extension process changes the sign of the number nor value of a number. Let us observe this one. Let us observe what this sign extension process. Okay. So what I say sign extension means placing small value into large register. How we can expand the sign? See now. See the now. So first notation we have sign magnitude, right? Sign magnitude we have. What is second notation we have? 1's complement we have. Third notation we have 2's complementation, right? 2's complementation. Okay, 2's complement. Let me take minus 6 is their number. Okay, minus 6. How to write on 3 notation? We'll observe. How to write the 3 notations on for this minus 6? We'll see. Okay, minus 6. Sign magnitude says what? You write this sign. What is sign? Minus 1. So magnitude what? 1, 1, 0. That's it. 1's complement, keep sign as it is. Invert 1. Add 1. 1, 0, 1, 0. This is a sign magnitude, 1's complement, 2's complement. Sign extension means suppose this is a 4-bit register is there. If I want to place into 8-bit register, okay, 8-bit register, I'll explain the purpose of extension also, but you see process of expansion, then we'll see the purpose later. Okay, expansion. So this is expansion. Okay. Sign extension or sign expansion, that is placing the small number into large register. 4-bit number I want to place into 8-bit register. So what is there? 1, 1. So what is the number is there? 1, 1, 1, 0. 1, 1, 0 is there. That 4-bit number you would write the 8-bit number. Very simple. If I ask question ma. So before this one, if I ask question, 123 number is there, decimal number is there. If I ask you express into 5-bit number, 5-digit number, how can you do it? Tell me. 123 is a decimal number, 3-digit decimal number is there. If I ask you to write in 5 decimal number, 5 digits, what you can do it? 0, 0, 0, 123, can you write it or not? Is the remaining same only? Does it change the sign of a number, whether positive or negative, or does it change the value of a number? No, remaining same. But same question if I ask you, minus 123 is there. If I ask you write the minus 123 in terms of in 6-digit number or 5-digit number if I ask you, then you will face a problem. Sir, how to write the minus? How to write the minus? The question comes, right? That's what we wanted to deal with now. Negative numbers now. Under sign magnitude notation, you write down the note point which I am going to tell. How sign extension process happens here? The sign bit is there. This is sign bit, right? Sign bit. Sign bit will move to the most, please understand. So remaining how many positions are there? 1, 2, 3, 4. Sign bit will move to the MSB position. Here it will move. This completely move. It will not copy, move it. Completely move. When it is moved, this position get vacant, right? So now we are placing 0. Remaining all extended positions are filled with zeros. Now final number becomes 1, 4 zeros, 110. 1, 4 zeros, 110. Definitely this is not going to be changed, please, value of a number or sign of a number. Still you see 1, 4 zeros, 110. See, what is sign magnitude? Sign. What is sign? Negative. What is the magnitude? All zeros followed by 110 give 6 only, minus 6 only. It is not changing the value. I hope it is clear. I am repeating the statement. For sign magnitude integers, when you are expanding the register, when you are expanding, sign bit simply move to the MSB position and remaining extended positions will be filled with zeros. That's it. So how expansion will happen for 1's complement? 1's complement number is what? Here is 1, 0, 0, 1 is there. Okay. 4-bit number, remaining how many? Remaining 4 positions you have to extend. Simply this sign bit, right? This is sign bit or not? This is sign bit. Sign bit you have to copy into all extended position. That's it. Same thing applicable for even 2's complement, 1, 0, 1, 0, right? So remaining 4 positions are there, right? This bit is copy, right? That's it. Now see, 1's complement number, 5 ones followed by 001. This entire number will not, please understand, neither change the value or not change the sign of n number, both are same. You can verify. Whatever this number represented, that is also same, the value is same, this value also same, nothing is changed. We will take the example. So now I hope you understand the sign extension process. Sir, what is the benefit, sir? Because in the computer system, when you are dealing with a 32-bit architecture or 64-bit architecture, 64-bit architecture, if I say in that architecture all register sizes and system bus sizes will be what? 64. Program counter size is 64. Like, but in the program counter you can place smaller number also, right? Example, accumulator is there, general purpose register are there, that register also 64 or 32-bit is there if it is 32-bit architecture if I use it. But in that 32-bit architecture, if it is a 32-bit register is there, in the 32-bit smaller number also can be placed or not, smaller negative number can be placed or not. When you place it, example, positive number, if a 32-bit register is, if I ask you to place the 10 is an integer, 1010, right, remaining 28 bits leftmost bits are zeros only, you will keep it. Am I right or wrong, all of you? Then if I ask you to write minus 10, if you write it, means the extension will go like this. Place in number and extend the sign bit, enter all position, so that value will not affect. So that happens in the computer system. Clear? Now let us see this number representation. This number so far we have seen. What are the notation? Three notation. Their representation. See what I am trying to say. Sign magnitude we covered, and we covered the 1's complement we covered, third one 2's complement we covered. All three numbers representation were for what? This is specifically used for signed numbers, right? Signed. It can positive sign or negative sign. So for them we will observe now, okay, value represent, value expression, and range will observe, range, okay. So we have seen now for positive integers, positive fractions we have seen, right. Similarly for negative integers, three notation, their representation value expression will observe, okay. I am writing let, you write n bit, okay, n bit binary number. So let me write in this next slide only. Okay, let n bit binary number, n bit binary number represents what is the represent? Fixed point signed integer, okay. Look this, what is the number I am writing? Okay, number I am writing B0, B1, B2, Bn minus 2, Bn minus 1, okay. This is n bit number, okay. B0 to B0 to Bn minus 1, okay. But what I told you, this Bn minus 1 is last bit, ms bit is there, right. This represents the sign bit, right, sign bit, this on the sign bit only, okay. For all three things we will see the value expression. First notation I will write it here, I will write a notation, okay, notations, and followed by value expression, okay, value expression. Look all of you now. The first notation is what? Sign magnitude, right? Sign magnitude, okay. What I said, one important point for sign magnitude. Sign magnitude will not participate in the computation. Means sign bit is there, right? Sign bit will not participate in the computation. So this bit is there, this bit I am saying. Bn minus 1 will not participate in the computation means what? So this not involved in the value expression also. So now see the value expression will be summation I equal to 0 to till n minus 2 only, So now each bit bi, you have to multiply, okay, multiply I. This word I hope you understand now. So I means what? So I equal to 0 to n minus 2 only. N minus 1 will not satisfy, okay. The sign bit Bn minus 1 is there. What the purpose of it? if this bit is 0, this bit is 0 indication, positive number. If this bit is 1 indication, negative number, that's it. That's it. I hope it is clear, all of you. I hope it is clear. The value expression for the sign magnitude representation here. Okay, what I am trying, this bit is not participating, that's it, I keep it outside. From B0 to Bn-2 only you have to consider it. This is a value expression. Like a positive integers I given, fractions also I given the value expression. Similarly for this you have to understand. Okay. So because I mentioned, what I mentioned ma? Sign magnitude and 2's complements are weighted systems. Sign magnitude and 2's complements are non-weighted system. And while 1's complement is non-weighted system, no value expression, please understand. It is a non-weighted system, no value expression. No value expression. Clear, all of you? Similarly, we will write the value expression for 2's complement notation. So second one is what? Third one is what? Sorry, this is second one, this is third one. 2's complement. 2's complement. Okay, value expression we write. One important point again, please note of it, all of you. Sign magnitude and 2's complements are weighted systems. What I said is sign magnitude weighted only, but sign bit will not participate in the computation. In the 2's complement notation, sign bit will participate in the computation with a negative weight. All of you write down this very important point. If you are using the 2's complement notation for representing the signed integers, getting my point? Now in this case sign bit will participate in the computation with a negative weight. So only sign bit is having the negative weight, remaining all magnitude bits are having the positive weights only in case of 2's complement. So now how to write this value expression? The value expression is going to happen, look, this summation I equal to 1 to 0 to till n-2 all positives, right? Bi into 2 power of I, positive only, plus last bit is having the negative weight, I am writing minus Bn-1, okay, getting my point, into 2 power of n-1. With last bit, right? 2 power of n-1. So I hope you understand the value expression for the 2's complement number representation. This is what 0 to till n-2 term we have taken having the positive weights, all are positive weight only. And last bit is what MS bit is having a negative weight. I hope it is visible. So I hope it is visible. If it is not done, let me rewrite it properly, little upside. Here I am writing the value expression for the 2's complement. Summation I equal to 0 to till n-2 I have to take it because so till n-2 the weights are positive and MS bit having the negative weight, right, plus minus Bn-1 last bit is into 2 power of n-1. This is the value expression for the 2's complement number representation. I hope it is clear. So now value expression we have seen for 3 notations. Similarly, we will see the range. Here I am writing the notation. So notations and range. What is the purpose of range? Range is covering the value of minimum to maximum. So what is the minimum value represent? What is the maximum value represent? It shows. Notation 1 sign magnitude. Notation 2 1's complement. And notation 3 what 2's complement. 2's complement. Okay. So what is the n-bit number, right? N-bit number. One point I said you. I said you, I hope you copied also. Sign magnitude 1's complement cover the same range and 2's complement have the different range. So what this point I will tell you. So just go and see this slide. In the slide you see. This slide is very important. One point I said you know before. Sign magnitude and 1's complement have the 2 pattern for 0. 0 is represented 2 ways. While 2's complement having the only 1 pattern for 0. Observe it, I written as zeros. 0, 0 is there, right? You see now. See this 0 0, here you see this is 1 0 0, here you see sign magnitude, this is 1's complement. Observe, plus 0 written all zeros, plus 0 written all zeros. When it comes to minus 0, 1 0 0 0, it is all ones. So I hope you all of you able to observe it. Sign magnitude, 1's complement, both are representing 0 into two different ways. Means it is occupying the two position for representing 0 only. Minus 0 plus 0 meaning is same only. A plus 0, A only. Yes or no? A minus 0 is A only. So sign for 0 sign will not impact. But when you use this two notation for representing number, 0 separately represented, minus 0 separately, plus 0 represented separately. But when it is comes to 2's complement, you observe, so plus 0 represented by all zeros, minus 0 also represented all zeros only. So you understand this 2's complement having only one pattern for 0 or not. So this is having two patterns. Now see, when it is having one pattern, nothing but negative side, one extra number can be represented or not. Yes. That is the reason I said you 2's complement better than the 1's complement in terms of computation also. Now if I do the comparison among three, which is the better or suitable to use the practical cases in the computer systems are 2's complement. Yes, 2's complement notation is being used for representing the negative integers in the practical scenarios. I hope the point is clear. Reasons I mentioned, two reasons I given. One reason is what? This has a more range. These two are having less range because having the two pattern for 0 only. And 1's complement slower than this 2's complement in terms of hardware. Because correction is required, for this correction is not required. So this is clear, right? So in the range, both are same range will cover because by having two pattern, this range would be more. Observe. I am writing the range here. Look this. So range means what? It has to cover minimum, maximum. So now I ask one question to all of you before writing here. Okay. Now tell me what is integer range? Integer range which we discuss, positive integer range 0 to 2 power of n minus 1, correct or not? Positive, 0, positive only. Now when you are going to use the 1's complement, 2's complement or sign magnitude, negative numbers also has to represent, right? Negative portion should be there, positive, negative both should be there. So now you understand among this range some portion you have to distribute for negative side, some portion you distribute for positive side. Half of this portion, please understand, half of this portion given for negative side, half of this portion given to positive side. Half of this portion of 2 power of, see, 2 power n minus 1. So this is half side 2 power n minus 1. So this way I will do it. Now see, now observe here. Sign magnitude range is minus 2 power of n minus 1. Here minus 1 will be there. Okay. 2 plus 2 power of n minus 1 minus 1. Correct. Similarly, 1's complement also 2 power of n minus 1 minus 1. 2 plus 2 power of n minus 1 minus 1. You can ask me question, sir, value expression is not there, how range is there? Simply it is taken from this sign magnitude. Whatever sign magnitude is, we are inverting. Whatever is range is, that is range only will be there for this. Now when it is comes to 2's complement, minus 2 power of n minus 1, 2 plus 2 power of n minus 1 minus 1 will be there. Here minus 1 won't be there. Please observe carefully. In the both the case minus 1 is there. Here minus 1 not there. That's what I was telling you. 2's complement negative side one extra number is there. If I keep minus 1, all range will be same, right? I am removing minus 1, nothing but you understand. This negative weight is more. Negative side range is more. So 2's complement having the more range than the 1's and sign magnitude. That's what I am trying to say. This is clear, right? So this, the previous slide, value expression of 3 notations. Now in this slide, the range of the 3 notations are given, because based on this basic questions we can get many times, 1 mark question being asked. The various gate papers, not only gate paper, even other exams also, the digital logic design subject is going to be common and COA is also going to be common. So these are the ranges questions we can expect. Okay, we'll see the example. We'll see the example, ma'am. We'll see the example. Look all of you, okay. You may get a doubt here. Suppose, so 3-bit number is there. Please understand, 3-bit number is there. What is the positive range for this? 0 to 7, right? 0 to 7 only, right? Yes or no? 0 to 7. Half of the number we have to distribute the left side, negative side, half of the number positive side, right? Yes or no, all of you? Now I am writing the first one, sign magnitude range. Look all of you, carefully observe negative range. So 0 to 7, how many numbers are there? 8 numbers are there, right? Yes or no? Now sign magnitude also covering 8 numbers only, but some are negative, some are positive. What are negative? What is the range? 2 power of 3 minus 1, right? 2 minus 1, minus 3. See, understand. It will go minus 3, minus 2, minus 1, minus 0, plus 0. Getting my point? Plus 0, plus 1, plus 2, plus 3. Okay. Total how many numbers are there? You see 1, 2, 3, 4, 5, 6, 7, 8. Positive integer, how many? 8 are there. 3-bit you can remember 8 only. But if it is integer, 0 to 7 number representation. If it is a signed numbers, minus 3 to plus 3 only. So now understand, in sign magnitude notation, 3-bit number is there, you cannot represent plus 7. Plus 7 you cannot store because negative side you went, right? Positive large number cannot come. So minus 3 to plus 3. See, here you observe now. Minus 0 also there, plus 0 also there. Similarly, if I take, ones complement notation, range. So here also minus 3 will be there, minus 2, minus 1, minus 0, plus 0, plus 1, plus 2, plus 3. I hope it is clear. I hope it is clear. Now see the difference. 2's complement range. I was theoretically telling the range. Now see, here is a minus 4, minus 3, minus 2, minus 1, 0, okay, plus 1, plus 2, plus 3. You understand? How many numbers are there? 1, 2, 3, 4, 5, 6, 7, 8 only. It is also 8. But what is the difference between this one? Negative side, you see one extra number is there. Sir, why minus? We don't have minus 0 plus 0. Only 0 only there. These two notice separately represented minus 0 plus 0. It is not represented separately one time. I shown the slide also, right? I marked, I shown you. That is the reason I am saying 2's complement covering the more range than this two negative side, not positive side. See, minus 4 to plus 3. 3 bits. You see the expression, 3 bits you substitute here. 3, 2 power of 3 minus 1, 3 minus 1, 2, 2 power of 2, 4 minus 4. Here, 2 power of 3 minus 1, 2, minus 4 minus 1, minus 3, so plus 3. So minus 4 to plus 3. I hope it is clear, all of you. Is it clear? So now we'll see some problems on in this area. So what I discuss, so number or data can be fixed or floating, right? If it is a fixed, it can be integer, it can be fraction. Now integer can be signed or unsigned, fraction can be signed or unsigned. First we have seen signed, unsigned integer, their range. Next we have unsigned fraction, their range. Next we represented signed integer, they represented 3 notations are there, their value expression, their range we covered. Now let's just see some problems. If I ask question, using 2's complement representation for 8-bit number is there, which of the following are the largest positive number and the smallest negative number? 8-bit number is there, what is the largest positive number? 8-bit number. What is the range for 2's complement? 2 power of n minus 1 2 plus 2 power of n minus 1 minus 1, right? N is almost 8-bit. So 2 power of 7, 8 minus 1, 7 nothing but what? 7 minus 128 2 plus 127 or not? So now their largest positive integer is what? 127. Negative number is minus this one only, right? Yes or no? This only, right? So option 3 is the right answer or not? Positive number you see, largest positive, smallest negative. I hope it is clear. Similarly, we will see another question. Minimum number of bits required to represent minus 61 in 2's complement form. Minus 61 is you want to represent. How many minimum number of bits required in case of 2's complement? How to answer, sir? How to answer this one? So we'll go with like brute force method. How many bits required? But once you practice by looking the number, you can answer directly. How, sir? Suppose 3-bit number is there, only integer. What is the range? 0 to 7. Correct. 4-bit number is there. 4-bit number. So let me write properly. So 3-bit number is there. What is the range? 0 to 7. Suppose 5-bit number is there. Positive range I am telling. 0 to 31. 6-bit number 0 to 63. Right. 7-bit number 0 to 127. 8-bit number 0 to 255, right. Similarly, negative range, 2's complement range if you see, okay. In this case, what I said you, 3-bit bits minus 4 to plus 3, yes or no? Here is minus. So now 3 is there, 4, 3 minus 1, 4 means 16, minus 16 to 15. Yes or no? It is 6 is there, minus 32 to 31. Yes or no? 7 is there, minus 64, minus 64, right? Minus 64 to 63. So 2 power 6 minus 1, 7 minus 1, 6 only, right? Minus 64 to 63. This one, in this case, minus 128 to 127. Yes or no? Now see, minus 61. So which falls under this range only, minus 61 can be represented. How many bits required? 7 bits required. 7 bits required or not? Yes, 7 bits required. See, like 61 falls here because 6 bits is there. 6 bits range, 2 power of 6, 2 power 6 minus 1, 5, 32 minus 32 to plus 31. But you cannot represent, you have to go 7 bits. Option 4 is answer. This way you can, reverse question, this way you can answer it. So look at another question. The 2's complement representation of a number in 16-bit is what? They given F7. What is the decimal value of this number? What is the decimal value of this number they are asking? What is the decimal value of this one? So now this F is the hexadecimal number, but right? But this 2's complement representation is there. So let me write the binary for this one. Binary outright 1 1 1 1 1 1 1 4 ones followed by 4 ones followed by 0 1 1 1, right? So this is a binary number, this given number is a binary number. Are you getting? The given number is a binary number, but what 2's complement form is here. They are asking what is the decimal equivalent to this one. They are asking what is the decimal number equivalent to this number. You know, a binary to decimal conversion. How to do binary to decimal conversion? How to do binary to decimal conversion? So each bit you have to multiply its weight, correct? But this is 2's complement. So 2's complement number you have to find out. 2's already 2's complement. 2's complement of 2's complement if you do, you will get original number. Are you getting my point? For this number, if you make it 2's complement, how to get the 2's complement? First to get the 1's complement plus 1 you have to add it. So that becomes what? Sign magnitude. So get the sign, then get the magnitude. That is a one approach. So the given number is 2's complement. Apply 2's complement of this one, you will get the original number. This is one approach. Other approach is that, so one important key point we notice from the 2's complement notation. In 2's complement notation, sign bit, this is sign bit, right? Please understand, this is sign bit, okay. Sign bit is having the negative weight or not? Sign bit is having the negative weight. Getting my point? Negative weight. Negative weight. So we can evaluate negative weight, take the negative weight and evaluate it. So I'll show the example. Before solving this question, let me take the example. Look this all of you. Suppose, okay, look all of you. 1101 is there. Suppose this number is there. It is not simple binary number. It is a 2's complement of a 2's complement representation of this number is there. Assume that. Now I am asking what is the decimal number? What is the decimal value of this one? You see there are two approaches. First you get the 2's complement of this one, you get the answer. Second approach is that what I said you, we know this sign bit having the negative weight, remaining bits are positive weight is there. Try to evaluate it. How the evaluation goes? You write the powers. 2 ways 1 into 2 power of 0 plus 0 into 2 power of 1 plus 1 into 2 power of 2 plus 1 into 2 power of 3. Which 3? Minus, this is minus weight like this. So, this value is 1 plus 0 plus 4 plus minus 8. Okay. Now, this will become minus 3. Yes or no? 5 minus 3 it will give. So, this way, but this much you should not do it. What to do? Look at the power. 2 power of 0 you write in 2 power of 0, 2 power of 1, 2 power of 2, okay, 2 power of 3. 2 power of 3 is minus 8, minus 8 will come, plus 4 plus 1. So, minus 4 plus 1 minus 3. So, minus 3 to represent, this way we can get it. This way we can get it. Suppose second example if I given 1 1 1 0 1 1, it is there, assume that like this. This number is in 2's complement representation. What is the decimal number? They will ask. What is the decimal number? Is this one. What I said you? Write the power. 2 power of 0, 1. This is 2. 2 power of 2, 2 power 1 is 2. 2 power of 2. 2 power of 4. 4 means 0 is the not right. So, 2 power 3, 8, 16, 32. Which 32 is minus 32? Minus 32 plus 16 plus 8 plus 2 plus 1. Okay. So, what this value it is give? What is the value it is giving? Minus 5. So, this is minus 16 plus, so this minus 8. So, this completely minus 8. So, this giving minus 5 directly. Yes or no? So, this way I can get it. One approach is that take the binary number, get the 2's complement of this number. 2's complement of 2's already given only 2's complement. Applying 2's complement becomes original number. So, that is another approach. Other approach is we know the property 2's complement number, in the 2's complement number sign bit having the negative weight. I am taking negative weight, remaining all positive weight, that is it. So, one more thing also we can observe here. So, this much calculation also not bad. So, this is fine. Take it another example. The example 1, this example 2, look at the example 3. 1 1 1 1 0 1, 1 is there, assume that this is there. Okay. If I ask you to evaluate this number means 2 power of 0, 1, 2 power 1, 2, 4, 8, 16, 32, 64, right? With 64, minus 64 plus 32 plus 16 plus 8 plus 4 plus 1. So, you simplify this one. If you simplify this one, what we will get? Minus 3 only will get it. Simplifying. See, you will subtract, right? Yes or no? We will subtract. So, this minus 30, this add and subtract minus 3 will get it. But lot of computation we did. So, this I will do it. This one only I will take another example. This example only I will modify some other way we can do it. 1, 2, 3 ones, 4, 5, 0, 1 is there. One more important property we observed from the sign extension. What is sign extension? Sign extension meaning what? What is the meaning of sign extension? Placing small number in large register. Placing small number in large register. So, look at this MSB bit. 1 is there. Before that, what is there? 1 is there. Before that, what is there? 1 is there. What is there? 1 is there. 1 is there. So, what I understand, this is copied from here. This also copied from here. This also copied from here. This also copied from here. So, my original number is 101 only. 101 number if I place in large register, sign bit will copy in the remaining positions or not? Please respond everybody. This 101 number if I place a large register, sign bit will copy into all the position or not? Same thing happen here. So, actually original number is what? 101 only. Evaluate 101. So, 2 power of 0 1, this is 2 power 1 2, 2 power of 2 4, minus 4 plus 1. This is minus 3 or not. See, after doing all the things also we got minus 3 only. But observing this point also we got minus 3 or not. Which is better? For a gate problem solving you have to go with this one only. Two important points I observed. One is what? 2's complement number representation, sign bit as a negative, all are positive. That is one thing. Second thing what? Many ones are there, you have to predict that small number placed in large register. You can ask me that how you detect this one is placed in small number in large register. This is only clue. This is MSB bit I know. Before that what is there? 1 only there. Before 1 is there. I am going with this one. This is original sign bit. it is copied into many places. Now, so this way you can reduce the number of computations. Now look at the question here. Now see here. This is a 2's complement number, right? This is a 2's complement number or not? They are asking decimal number, they are asking. What the decimal number of they are asking, correct? Yes or no? Now see, so now next this MSB bit, sign bit, this next one is 1, it is copied from here, this is copied from here, this is copied from here, like this you understand. So this is copied from here only. So original number would be 10111. This only original number placed in large register. So evaluate, this is 1, this is 2, this is 4. 8, 16, minus 16 plus 4 plus 2 plus 1. How much? This 6, 7, subtract 7, this gives minus 9. Yes or no? So minus 9 is answer. Option A is the right answer. Sorry. Minus 9. Option 2 is the right answer. Minus 9, right? If you simplify directly also will give same answer. But if you know these two properties, getting answer becomes very, very easy. Because these questions are, this type of question frequently we have seen the GATE paper. I hope it is clear, all of you. Okay, ma'am. Some more, suppose reverse also they can give it. Reverse also they can give it. Please understand. Okay. Another type of question we can expect here. Another type of question we can expect. Suppose minus 13 is there. Please understand. They are given minus 13 decimal number. They asked us to represent in 2's complement form. So if they asked us to represent 2's complement, minus 13. How to represent minus 13 in 2's complement? Question comes. The simple approach is first you write the sign magnitude. Simple approach is write the sign magnitude. Writing the sign magnitude for this number becomes easy. Sign is what? Minus 1, 13 how to write? 1101. Yes or no? Sign magnitude. So get the 1's complement. How to get the 1's complement? Keep sign bit as it is. So invert these bits 0, 0, 1, 0. Now third one 2's complement. What is 2's complement? Add this one 1, 0, 0, 1, 1. Add 1 to this results. So now this is the 2's complement of minus 13. 1, 0, 0, 1, 1 is the 2's complement representation of a minus 13. Clear all of you? If I ask question, second question. So represent the minus 21 2's complement. 2's complement. One way, what is the one way? First to get the sign magnitude. How to get the sign magnitude? Minus is 1, magnitude 21. So I hope you learn the conversions, number system conversion. What is the decimal to binary, binary to decimal, binary to octal, octal to binary, and hexadecimal to binary, binary to hexadecimal, decimal to hexadecimal. These all types of conversion you might have learned. So I hope you can write 21 into binary. But short form how you can write directly, sir, without the division approach you might have learned, or short form also you might have learned. You see how to write it, 21. You try to remember some powers, 2 power of 0, 2 power 1, 2 power of 2, 2 power 3, 2 power 4, 2 power 5, like this. So 2 power of 4 how much? 16. So I am taking the 2 power of 4 high. 16. So 2 power of 4, 16. 2 power 3, 8. 8 position making 0. 2 power of 2 position is 1. 16 plus 4 is 20. So now what am 2 power of 4, 2 power of 3, 2 power of 2, 2 power of 1 I will make 0. 2 power of 0 I will take 1. See. So this is 2 power of 0 weight, right? 2 power of 0 value is 1. 2 power of 1 value is 2, making 0. 2 power of 2, 4. 4 plus 2 power of 3, 8. 2 power of 4, 16. 16 plus 4, 20. 20 plus 1, 21. So 1, 1, 0, 1, 0, 1 I can write it. So second one is the 1's complement, right? 1's complement. Keep it sign as it is. Invert 0, 1, 0, 1, 0. Third one is the 2's complement. What is 2's complement? 1, 0, 1, 0, 1, 1. Add 1 it is. This is 2's complement representation of minus 21. So every time you have to, I am going what? Sign by 1 and 2's complement. So can't I do it sir directly? Yes, we can do. Example 3. Example 3. Suppose if I ask you minus 23, decimal number represent 2's complement without going to sign magnitude 1's complement. Directly how can I do it? Simply same property I can use. What is property? So the weight, so sign magnitude, so 2's complement is what? Weighted system in which sign bit is having negative weight. So that point I can use to represent this number. Look this, how to write it. 23 is there, powers you remember, 2 power of 0, 2 power of 1, 2 power of 2, 2 power of 3, 2 power of 4, okay, 2 power of 5, okay, like this I am going, assume that, 2 power of 6, see. So till I will go, how sir, how I am going, 2 power of 0, 1, this is 2, this is 4, this is 8, 16, 32, okay, see. So look at this number, suppose if I ignore minus 23. So now look at the powers, greater than 23 what? Next step to 23 is 32 only, right? Till 32 you have to go. Till 32 you have to go, okay. Suppose this 32 position, 2 power of 5, 30 position, if I keep it 1. So now can I get the negative weight or not? You will get in minus 32 or not? Tell me, think yourself. See, since 2's complex representation, sin beta has negative weight. Suppose what I am trying to say, this position if I plot it 1, I get the weight. How much weight? Minus 32. But I need to remember minus 23 only. For minus 30, how much positive value I should add it to get the minus 23? How much should I add it? So 7 plus 2, 9. So 9 if I add, can I get 23 or not? Yes, 9. So 9 means what? I have to make it 8 position. 8 position 1 and this is 1. Remaining positions are 0 only. So this is a way I can get it. This is a way I can get it. If you do with a sign magnitude way, you will get same thing only. Get what I did? What is the clue? I will take one more thing I will get. Suppose if I ask you minus 51, if I ask to represent minus 51, what I said, you look at the 51, next to higher position you go. 2 power of 0 value 1, then 2, this is 4, this is 8, 16, 32. So I am going to 64 because 64 greater than this 51. So for this position if I make it 1, so you will be getting minus 64. Further some positive value you add to get the minus 51 here. X, how much I should add it? 9 plus 4, 13, right? X equal to 13 or not? 13, how to get the 13? So 8 plus 4, 12, this is 0, 0, 0. I hope you understand. 8 plus 4, 12, 12 plus 1, 13. 13 you remove from minus 64. So minus 64 plus 13, how much? 1, 51. Minus 51, right? Yes or no? So this way I can write it. I hope you understand. Now this you understand. 2's complement representation of minus 51. This way we can understand. So if the decimal number is given, they ask us to represent into 2's complement. So though with the 2-3 example, we have learned represent of 1's complement, representation of 2's complement, representation of sign magnitude. So conventional approach and shortcut method also we have seen. This is one type. Other type, they will give the binary form, 2's complement binary number they will give, they can ask us to get the decimal value. That case, 2's complement of 2's complement you will get, other way use some shortcut method which I discussed, so you will get it. So this way we can answer it. So now till this point, we have learned, we have covered the basics which is required to understand the floating point. What are the basics? I am just concluding. We understand representation of the signed integers, unsigned integers, fractions we have seen, their ranges, all the possible ranges I have given. All of you, I am requesting you, write down the note of it, all the ranges which I have given, which are useful to understand other things, and sometimes direct questions also get. Fine. In the next session, which I schedule, that is 5th April, same time at 4 p.m, we have another session on this floating point area. So exactly the floating point area we start. Fine. Like every week 2 sessions will be there, like the schedule already you got it. So kindly attend into live sessions, all of you. So I hope you enjoyed thoroughly this session. This session definitely is going to be utilized to you, like useful to you, understanding the other topics also, because basics I would like to cover. And those who are not watched completely, please go and watch from the beginning. Definitely is going to be beneficial for you, all of you. Thank you so much, all of you, ma'am.